Hello everyone, welcome back to my channel. So in today's video we will understand let's see color spaces with OpenCV. I'm super excited to take you on this let's say colorful journey. So as you can see here we have several let's see many color spaces like red, green, blue, BGR and HSF and gray and also lab, and we will go through each step, I mean each color space, and see how to convert between this part and this color space and this color space, and when to use this color space, and what is the benefit of converting this into different let's see color spaces. And I will show you let's see example. Already the code is already here, live coding. Sorry for this, I have let's see a hand pain. So before diving into this color spaces, let me ask you a question. Have you ever wondered why photo editing apps have so many color adjustment operations, or why let's say some color look different on your phone versus your computer? And that is the color are not just what we see. They are the data that can be represented in a different ways. So today we are going to unlock the power of color spaces using Python, of course, and OpenCV. By end of this lesson, you will, yes, by end of this lesson, you will understand how computers see the colors, and also how to convert between these two different color representation, and most importantly, how to use this knowledge to solve, let's say, real image processing problems. And mean, for instance, when to use HSF and when to use red, green, blue, and etc. So let's start with this here. So before that, we need to set up our environment. So because this matplotlib, it's not already installed in my PC. I mean, I have already done this before the recording, but it wasn't in this YAML file, toml YAML file. So now, as you can see it, it's here, and also I have added this. I will show you why I have added this. So now let's say I have imported, I mean, add the matplotlib or install matplotlib in matplotlib in my project, so I can use it. So now I have imported this stuff, matplotlib. Why I have added matplotlib? Because matplotlib is let's see, I'm not quite sure if this is right, but this is the best let's say visualization lib. Of course, there are many, but let's see. Let's see. Not just to see this is the best. And now let's see what are the color spaces. So before we load any images, let's talk about what are the color spaces are. So a color space is essentially a system for representing I mean image colors in numerically. Think of it as I don't know, as a language for describing colors in a standardized way. So we already discussed this, how to see the colors, and the colors are only the values of each channel represented. For each channel we have, or each channel represented in a different class. Let's see, represented in a different values from 0 to 255. And let's see here, the color space is essentially a system for representing color numerically. And can anyone name a color space that, I mean, they might have heard of? So the color space are, I will already said, the red, green, blue, uh, uh, blue, green, red, and this is the default of OpenCV, and this is the default one of the PIL or Palo packages. And we have seen this, of course, OpenCV stuff. So red, green, blue is probably the most familiar, let's see, one. I think so. But there are many others like HSF, Lab, and YCRCB, each designed for specific, let's see, purpose. And why we need these different color spaces indeed. So it's like having different tool in your toolbox. Some tasks are easier in one color space than the other. So want to take a specific color. So if you would like to detect a specific color, then HSV might be the best choice. Need to enhance image contrast, then lab could be the perfect one. Just displaying an image, then red, green, blue is probably the best one. So now let's load some images here. If we already have seen this, so let me just load this image. I have already show you how to write this code uh, in the previous session, and you can see here I have loaded the image. It's only one image. Now I convert the image into red, green, blue, so I can display it in this matplot. So as you can see here, I have maybe this is new for you. So this is matplot. I have imported the packages here, and now I have created a figure, which is a figure like this. For instance, this here, it's 8 by 8, and I have just plot dot m show, and you have also the title. You can see the title here, and the text. I mean, the axis is off, which is, let's see, if I remove this, it can show you the numbers between x and y. I mean, x axis and y axis. But for displaying the images, it's not needed to have this because it's not, let's say, meaningful, maybe. Or and this is, let's see, how to read the images. So let's see the color spaces, the green, I mean, blue, green, red color. So let's just explore the color space by splitting our images into individual color, into individual uh, channels. And you can see the OpenCV is providing a function we call split, and you can split the images into three different channels. The BGR, I mean, blue, green, red. This is the default when we load the image. And if we see here, we can try to plot this. I mean, we can see here, if we create a plot or figure with four columns, and this one is four columns, and you can see the first column is one, I mean this, two, three, and four. And I'm trying to display the image itself, the original image, then the blue, green, and red channel. And as you can see here, this green blue channel are only let's see one let's see two-dimensional matrix. So this is only one channel. I mean, this is the original image, and this original image we have seen these colors. Why you have seen these colors? Because it combine all of these values. So that's why we have seen it as a color image. And I'm quite sure that you might see this blue, green, red are the same, but fortunately the red somehow it has a little bit white colors, as you can see here. This one is different from this, and of course you can try to print some values, let's see, or pixel value, to see what is I mean the differences. And if now you create this image, for instance, this is the blue, right? And if you now create make it as a three channels only with this, and for instance the blue is this values, and the green and red will be 0 0, you can see it as a blue image. So I mean, in this, let me just with yeah. So you can see in each channel is a 8-bit grayscale image with values from 0 to 255. Yeah, so you can see the 0 is represent no intensity, and the 1 is represented maximum intensity. And yes, so now let's see, try to convert between color spaces. So now for the real power of let's say that the power for of OpenCV is converting between color spaces. So we have already used. I'm quite sure that we already seen it in the previous video that we use CV to dot convert colors. So conf CVT is convert, stands for convert, and to convert, for instance, from BGR to RGB. But there are so much more to do. Let's see, indeed. And let's say we move to this, for instance, the way of converging a code, specify the type of conversion to perform. And let's see here we have the gray color space. So we have the image already loaded when we have loaded the image, which is in this format here, BGR, and we need to convert it to grayscale. Now, if I want to see it, uh, the grayscale image, and you can see here this is the original one and this is the grayscale image, and I'm quite sure that we already see this. So why we need this here tight layout? It's just to make it a good let's see representation. So the removing the spaces between these two images. Let me just show you, so you can see it's there are many space, but this is try to justify this the space. Okay, so notice something here interesting about the shapes. The original image has three dimensionals. I mean, of course, height, width, and channel. But the grayscale image has only two. So let's try. You can see the the grayscale image has this shape, and the color image has three channels. So this means we have three channels here, but we have only one channel here. This is because the grayscale uh, represents each pixel with a single value instead of three different values, red, green, blue. So why might we let's say want to convert an image to grayscale? Why we need to convert it to grayscale? So sometimes grayscale are used to intermediate step in many algorithms because it simplifies the image while retaining important structure information. And this you will see it when you try to detect edges. You have to convert the color images into grayscale images. And it's also useful when when color see information are not necessary for the task that you know that you have. But for the deep learning, we have most of the algorithms, let's say most of the architecture of backbones use color images. I mean, trained on, of course, on real images. And do you know the conversion from green, let's see, blue, green, red to grayscale is not a simple, let's see, average. So someone will ask, of course, how do we get, for example, here we have three values. For each pixel, we have three values. But how we come to only one value? It's a good question if you ask this question. So for this, it's use the weighted sum account of human perception. Is the formula? Yeah, you can see here. So for instance, you have this red. This is multiplied it by this value, plus multiply the green by this value, and also by blue. And sum all of this up, you will get only one pixel. This is the gray scale. These weights reflect that human eyes are more sensitive to green light than red or blue. So why we came with this formula? This is I can't see why, because this is, let's say, somehow physics stuff. Okay, so but when you ask, for instance, how do we get from three channels to one channel, so you use this formula here. And now let's explore one of them. Let's see, favorite color spaces, HSV, or called hue, saturation, and value. And let me just run this. And of course, there are many. There's information here you can read. For instance, the hue, the color type, it's like red, blue, or yellow. In OpenCV, it's range from 0 to 197. In OpenCV, is from 197 to the saturation is the intensity of the color from zero, for instance, gray, to 255, which is pure color. And the value is the brightness from zero as a black to 255 as a white color. So let's do this. And this is our original image, and this is the H, this is the S, and this is the value. So why am I separating this color for from brightness to let's see, useful? So the separation makes HSF perfect for tasks like color-based object detection. So let's try to detect if you would like, as we mentioned in the beginning, if you would like to detect the colors, you have to convert the image into HS color space. So, and also the separation makes HSV perfect for tasks like color-based object detection. So this is the code here, and now let's see somehow add a practical example isolating a specific colors. So for instance, here we have. Let me just see. Yeah, I think this one is already converting from BIG to this color space, and here we split the three colors, and he just showed it's normal. I mean, there's no, let's see, fancy work beyond this. And this one here, so you can see we have isolated just the red part of the image. So let's see, and this one here. So we defined, let's see, a range of the low red. I mean, yeah, by the way, the red, it has low and upper value. Red and lower and upper red. And here we try to create a mask. This is the bitwise. It's applying the mask, let's see, to the original image, which is 1, and this is converting to the back to the image to the RGB, and here we display the image. Okay, so now this is the technique is used for everything. Let's see, for traffic light detection and self-driving car to medical, let's see, image analysis. So this is used, for instance, if you'd like to detect a car. So let's see, for instance, here we detect the red color. Okay, so now the next color space is lab. So now let's explore what is the lab space and which is designed to approximate human vision. By the way, all of these, let's see, guys, these colors are somehow designed or by some physics guys. And yeah, so here we have the OpenCV already provide everything for us, so we just know what we'd like to use and when. So this is the lab, and we converted, of course, split the channels and represent the channels, and you can see here L, A, and B, and L is represent lightness from 0 to 100, and A represent the green red components, and you can see from minus to plus, and B is representing blue yellow components. I mean, of course, if you are interested in more details, I can give you a reference for this, so you will be, let's see, somehow familiar with this if you would like to go dive. And let's see now, combining. Yeah, and this is the one. It's YCRCB color space. It's like commonly used for video and image comparison standard like JPEG, MPEG, and also it separates the luminous components from the Jonas components. So Y is represent the brightness, let's say brightness, and CI is represent the red difference, and the CB is represent the blue difference. So honestly, guys, I haven't used, let's see, this color space here. So mostly I'm just using the red, green, blue, OpenCV, and also the HSV. And you can see this is the original image and this is the conversion between these three color space. Okay, now we need to compare between the color spaces. So let's somehow make, let's say, a side by side comparison of the color spaces we have already explored. And let me just see if we can. I think this is already discussed, and here we have 12 cell, or let's say 12 figure, and this is the original image, and converting to the grayscale HSV lab, and this one, and here we split the who from this, and here we have only the L or lightness from lab. This is the Lorentz channel, and this is the red channel from the RGB. Okay, and now let's see what are let's see what is the amazing journey. Let's see how to summarize when to use H1. So red, green, blue, or blue, green, red is a default color space for most image processing library. And it's good, let's see, for displaying images and also general purposes processing. And as you see, this blue, green, red is the default of the OpenCV. And while the red, green, blue are the default for the pill or pillow. So the grayscale image, when color information want to use this, when color information are not necessary, and also for edge detection as we discussed. I mean, of course, we will see what is the edge detection, what is the contour findings, and in the really advanced, let's say, sections. And also to reduce computational complexity. If the colors are not needed, so with this we will remove it, and by that we reduce the computational complexity. And HSF for color-based segmentation and object detection. When you see it, when you need to isolate, let's say, specific colors, or let's say an environment with varying lighting conditions. And yeah, and here I have added, let's see, a table to see what is the, let's see, that's why I have added here, install the table blade. So here you can see this is the conversion, and this is the OpenCV code. From blue, green, red to red, green, blue, you use this function. And just to make it, yes, just to make it, let's see, as in a table here. So we have covered, let's see, much, let's see, around the color spaces, from understanding what color spaces are to converting between them, and also applying them into, let's see, which problems, real problems we can. So I think, I hope this session has, let's see, opened our eyes, or your maybe your eyes, to a colorful word images processing. Remember, these techniques are not just academic; they are used every day in applications, from smartphone cameras to medical imaging to, let's say, self-driving cars. And thanks for watching. And if you like this video, please subscribe into my channel, like the video, and also if you have, of course, any questions, just drop them down in the comment below. I also add the references here, so if you would like to be, let's see, more deeply in this field. Thanks for watching, and see you next time.